recording. Yeah. So, okay. In today's lecture, I hope you can see the screen, right?
Yes, sir.
Okay. So, in today's lecture, we'll be dealing with an example on a turbofan engine. So, consider that we have a turbofan engine. So, okay. So, what all things are there in the turbofan? Can you list them? So, starting from the diffuser, then
Compressor,
yeah, compressor.
combustion chamber,
Yeah, right.
turbine.
Okay.
Then, if there is an afterburner, so
Okay. So right now I'm talking about a turbofan engine.
okay, nozzle,
Yeah, nozzle. Uh, are you missing something else? Uh, major feature that is there only in a turbofan engine.
roof, and okay. After the I can't recall actually.
Okay.
Then
The
there is
fan
a
itself.
fan to intake. Okay, yeah,
Okay, the
yeah.
fan itself, right?
Yes, sir.
Okay. So, okay. Before, okay, yeah. Let me define the problem first. So you have a turbofan engine. Okay, that is now cruising at Mach number 0.75, and the mass flow rate of the air is given, that is 74.83 kgs per second. That is the mass that is going uh, inside the no, this is the total mass flow rate that is going inside uh, the engine. Okay, so this is 74.85, and you have a pressure ratio compressor. Okay, for compressor you have a compression ratio of 15, and the efficiency of the compressor is given as 88%. Okay, so okay, let me draw the engine now. So this is, since it is an axisymmetric, I'm just drawing in the half part. So you have the fan, you have the central shaft. So this is fan. Then you have a bypass duct. Also, in the bypass duct can be divided into two streams. I'll tell you why it is so. So these are the compressor blades. These are the compressor blades. Then followed by the combustion chamber. Okay, and then you have a turbine. Turbine. This okay, and okay. After this, you okay. Let me shift these things to this part. Okay, followed by you have a mixing area, mixing thing, mixing duct, where your hot stream which mix with the cold stream. This cold stream is there to cool the engine. So after, when you are having a combustion chamber, so you must have a liner which can act as a cooling duct for the combustion chamber. So there, this is why you have some split in the uh, bypass air. So okay, what is a bypass air? We'll get to know. So after
Sir,
that,
something like that is also used in afterburners, right?
uh,
Like the cool air, so that air is ignited
Yes.
using fuel.
Right. So
Yes.
for the major difference between the burner and without afterburner is so at the nozzle part. So okay, let me draw this. So yeah, so you have a nozzle in a this is a without afterburner. You have a cold stream and you have a hot stream that is coming out. Okay, this is from the combustion chamber. So let us see what happens in a afterburner. You have a long duct, you have this, and you have another um, injector here. Okay, so and you have this axis again. So after the cold stream, so this is from combustion chamber. This is cold stream. So now after this, what we do is we again inject the fuel. Okay, so some of the okay, you we have a longer duct that in this again the temperature increases. Okay, and this flow this expands to the nozzle. In the previous case, there was no fuel that is getting injected before the nozzle. Is it fine? This is with
Yes, sir.
this is with afterburner. I hope this answers your doubt, right?
Yes, sir.
Okay. So if you see the TS diagram, you would see this difference. So this is the E- okay. This is compression. This is combustion chamber. Then okay. Then we expand to the turbine. Then we again raise the temperature in the afterburner, right? And then we expand to the nozzle. Okay. This is for the afterburner. Whereas when you do not have a afterburner, you expand only till this part. This is turbine. Okay, and this is nozzle. Whereas if you have afterburner, you can expand more. Okay, it is it fine?
Yes, sir. Thank you.
So let us move ahead. So the compressor efficiency and pressure ratio is given. Now the split ratio and bypass ratio is given. Bypass ratio is given as 3 and split ratio is given as 0.25. Uh, as we go along, I'll let you know what all these terms tell you. Now the efficiency of the fan is given as 90% and the calorific value of the fuel is given as 41,400 kilojoule per kg, and the total temperature total temperature after the combustion chamber is given as 1389 Kelvin. Then the efficiency of the burner is 91%, and the pressure ratio across the burner is given as 95. The turbine efficiency is given as 85%. 85%. The duct. Okay. The duct has a the duct that is there. This duct. Uh, this one. This duct uh, has a total pressure ratio. The total pressure ratio of 97, 0.97, and it is given that the nozzle that is used for expanding the hot stream is a CD nozzle. Okay. Yeah. So it is given that it is a CD nozzle, and the fan nozzle is convergent. This is CD. Okay. So the okay. Now the efficiency of the nozzle for the hot stream is 0.96, and efficiency of the nozzle for the cold stream is 0.95. Yeah, and the total pressure recovery of the diffuser, the pi d, is given as 0.92. Yeah, and the efficiency of the shaft is given as 99.5%. Okay, so okay, and it is required. What is the thrust and TSFC? Okay, so maybe you can look into the question again. Uh, I hope it is visible. So, okay. So there's a turbofan engine which cruise at 0.75 Mach. The master rate of air is given. Compressor efficiency and pressure ratio is given. Split ratio and bypass ratio is given. For a fan, the efficiency is given, and the for burner, pressure drop, efficiency, and the calorific value of the fuel is given. The then efficiency of the turbine, efficiency of the diffuser is given, and for hot stream and cold stream, the efficiency of the nozzle is given. The the diffuser pressure ratio is given. Whenever we say this thing, this is total pressure ratio. Okay, and also the efficiency of shaft is given. Okay, so now what we have to do is we have to find what is the thrust and TSFC. For this, let us simplify our analysis, and let us define the stations. So zero signifies the ambient condition, and one signifies the condition at the diffuser. This is the diffuser. Okay. Uh, then two. Okay. Between one and two, there is a diffuser. Between okay, let me define in this only. So let me define here. Okay, zero signifies this ambient condition. This is one. Okay, before the inlet, this is one. This is two. Then you have yeah, you have after the combustion chamber, after the compressor. This is the compressor. This is fan. Then you have four. You have five. After mixing, say it is six, and yeah. Uh, okay, one more thing is required. I think let us call this thing as seven, and after the nozzle it is nine. Yeah, one, and this is 8. So I hope the numbering is clear to you. The stations, how I have defined.
Yes, sir.
So we just have to find what is the total temperature and total pressure at all the stations. Then we in all the questions which you see for this gas turbine analysis, you need to find what is pressure at the exit, velocity at the exit, area at the exit. Okay, because at the end you have only the equation for the thrust, that will be that will give that contains your m dot a into v exit minus u inlet plus p exit minus p ambient minus p ambient into a exit, right? So you need to calculate all these parameters for this. Okay, so right. So let us start with the analysis. So between 1 and 2 there was a diffuser. uh, मेरा टीए चल रहा है, मैं बाद में बात करता हूँ. Okay, so yeah, okay, this is diffuser, then followed by the fan. Then from fan there are two streams that are going through it. One is the nozzle, cold nozzle, and other part that is getting diverted into the okay, this is a compressor, right? This is after the compressor we have combustion chamber. Also some of the mass that was uh, bypassed from this fan is going into this the cooling duct. So this is the duct part. So yeah, so this is the combustion chamber followed by the turbine, and this is okay. After this turbine, uh, this and this part mix. Uh, this is a mixing chamber. This is a cooling duct, and then followed by a CD nozzle. I hope this is clear to you. This is a hot.
Yes, sir.
Huh?
Sir, the cold nozzle surrounds the hot airflow, right?
Yes, yes.
Okay.
Okay.
And it has vortices in that.
Vortices, yes. Yeah.
Okay.
So whenever you have a shear layer, you will be having the okay, the shear layer. So you have this okay, you have this engine, and that is giving you inner part is giving you hot air, and the top portion is the surrounding annular part is giving you the cold, right? Cold jet. This is the hot jet. So whenever you have a difference in the density or the velocity, so you have something known as shear layer formation. Shear layer. Okay. So so in a shear layer, if you see closely, so there are small vortices that are there. So in between, if you see, there will be a shear layer, and the vortices will be inside it. Okay. So let us move ahead with this, and let us start with the calculation for the diffuser part. Okay. So let us calculate what is the velocity of at the inlet. So this will be Mach number of the aircraft times gamma r T ambient. So okay. So right. Um, okay. Also, it is given that uh, it is flying at a sea level. Okay. So at sea level, the temperature TA is 288.16 Kelvin. Uh, so with this, you get the V inlet as 255.5 meters per second, right? So yeah. Then coming on to the why we require this velocity, because in a thrust equation we'll be needing this thing later. So coming on to the total temperature, mm, T naught not T naught specify the stagnation property and naught signifies the station. So this is T naught by T is equal to 1 plus gamma minus 1 by 2 m square. So this gives you 288.16 into 1 plus 1.0.4 by 2 into 0.75 square. So if you calculate this, you will get the T naught A as
So we
yes.
have Vn, right? So from that we can find the Mach number.
Huh. Come again, please.
Sorry. We have velocity n, right?
Yes.
So we can use also that, right?
Yeah, you can use it. So
Like
for
1 plus velocity square upon 2 into Cp. Sorry,
right. So
Cv.
it is just T naught is equal to um, T plus V1 square by 2 CP, right? You can use this. So
Yes, sir.
this equation is just another form of this. So if you
Huh.
replace this CP with the okay, so if you see this equation, right? So this is T plus velocity can be written as m square gamma RT, right? So this is V velocity is Mach number into under root of gamma RT. V square is this, and 2 R gamma minus 1 into gamma, right? So this part cancels off. If you take t common, if you take t common, 1 plus gamma minus 1 by 2 m square. So this is the same equation. This is the same thing that uh, this is just a conservation of energy, right?
Yes, sir.
So let us okay. So right. So let us calculate what is T naught two, T naught one, and T naught two. I hope this is clear to you that it will be equal to the T naught itself, because we are not adding any heat between 0, 1 and 2, right? Neither any type of work is done. So the stagnation temperature will remain same. Okay.
Yes,
So
sir.
this will be equal to 320.6 Kelvin, right? Now let us calculate what is uh, total pressure P naught by PA is 1 plus gamma minus 1 by 2 m square gamma by gamma minus 1. So if you substitute this, so you will get so with this you will get around this the ratio between this P bar PA is 1.4522. Okay, so okay, and also it is given that okay, let us calculate what is uh, so mm, um, also it is given that the pressure ratio across the diffuser is given, right? So pi d. So you see that the pi d pressure ratio across the diffuser is given, that is 0.92. So if you substitute pi d is p naught 2 by p naught a, which is 0.92, which comes out to be 1.3360. So P naught 2 is 1.3360 into 101.325, which gives you 135.3 kilopascal. Uh,
So
so
that's the pressure after diffuser, right?
this is the pressure after diffuser. Yes.
So then, why did we took temperature same, like,
Okay.
because the velocity will decrease, right?
Yes.
So uh,
Okay.
so so
This is not the okay. This is not the static temperature. This is your stagnation temperature. Okay. So I okay. Let me tell you why it is so. So if you do an energy balance between zero point 0 and zero point 0.2, so let us write a steady flow energy equation. So this will be Cp T1 plus V1 square by 2. So there is no heat transfer, and also there is no work done. So it's Cp T2 plus V2 square by 2, right? Is it fine? So this is a stagnation temperature. So if you divide this equation by 2 Cp T2 plus V2 square by 2 Cp. So this is your stagnation temperature, T01, and this is T02. So this is what we have written. We have not equated the static temperature here. So static temperature was 288.16, right? So we have only written that T01 is equal to T02 is equal to T0.
okay, sir.
Just, yes, when you talk about the static temperature, they will be different at different point, because the velocity will be decreasing and the temperature has to go up. Okay, so so right. So let us move ahead, and this is P naught 2. Let us write up, across the compressor now. So now it is given that P naught 3 by P naught 2 is just the compression ratio, which is given as 15. Okay, so P naught 2 is 135.3 kilopascals. With this, P naught 3 can be calculated as this will be 2030 kilopascal. Okay, now we have to calculate what is T naught 3. Okay, so for this, let us draw a TS diagram. So this is your P naught 1, this is your P naught 2. Okay, not sorry. This is your P naught 3. This is your P naught 2, and yeah, the compression ratio is given. We have to find what is 1 minute. So this is okay. So uh, the temperature. This corresponds to T naught 2. This is T naught 3 dash. This is T naught 3. Okay. So T naught 2, T naught 3 dash by T naught 2 is P naught 3 by P naught 2 to the power gamma minus 1 by gamma. Uh, you have this. So uh, okay, also you know, okay, this is 15 to the power 0.4 by 1.4, and T naught 2 is 320. It is 320.6, right? So this is T naught 3 dash. Also, uh, yeah. Now you also know what is the efficiency of the compressor. Efficiency of the compressor is defined as uh, T naught 3 dash minus T naught 2 by T naught 3 minus T naught 2. Okay, so T naught 2 plus T naught 3 dash minus T naught 2 by efficiency of the compressor. You have T naught 3. So if you substitute this T naught 3 dash from here in this equation, and you have what is T naught 2, you and also the efficiency of the compressor is given in the problem, which is 88%. Okay, so with this you can calculate what is T naught 3. So T naught 3 uh, with this you it will come out to be 724.7 Kelvin. So now let us write the values in the equations now. So this is T naught, which was 320.6 Kelvin. Temperature at this section was 288.16, right? Pressure was 101.3 kilopascals. P naught was, I guess it is, yeah. So okay, so this is 1.4522 times. Get the calculator now. So, so this is 1.5 1.4522 into 101.325. So you will get this thing as P naught as 147.1441 kilopascals, right? So after the diffuser, the temperature is unknown, but T naught is known. This will be equal to 320.6 Kelvin, and P naught we have calculated as 135.6 kilopascal. Can somebody tell me why the pressure has what is the reason for the loss of this stagnation pressure?
Frictional losses.
Yes, right. So this is because of the friction losses. So okay. So coming on to the
Sorry,
compressor, huh?
I have a doubt, sir.
Huh.
So, but the stagnation temperature remains constant, right?
Yes, yes,
But both the stagnation temperature and the pressure, both are a function of velocity, right? So in
yes.
that case, how only pressure is dropping, but the stagnation temperature remains constant, sir?
Okay, okay, let us consider this, right? So if you have okay, so consider this. So you have a duct and you have a boundary layer that is getting formed. Okay, so velocity goes down. So what is happening? If you consider a small packet of a fluid, okay, that is moving with a bulk velocity of v, okay. So what happens when it comes in this region? the bulk velocity decreases, whereas whereas the energy will go. So you are not extracting any heat, or nor you are giving any heat to the system. Okay, so the velocity, that is the kinetic energy that is decreased, goes into the internal energy, which increases the temperature. Okay, but the sum of the sum of velocity times this remains constant. Okay, velocity goes down, temperature goes high, but this term remains constant, and this is our stagnation temperature, right? So this is the reason why temperature remains constant. Okay.
Okay, sir. In the case of pressure, also same thing happens.
In the case of pressure, okay. So okay. So let us see why the pressure is decreasing. Okay. So now I hope. Okay, the pressure. Right. So this pressure is just P1 plus gamma minus 1 by 2 m square gamma by gamma minus 1. Okay. So yeah. So as your, okay, this is P naught, right? So okay, as the temperature increases, so now we have seen that the temperature increases, the Mach number will decrease, right? So Mach number is velocity by gamma RT. Temperature increase, velocity is decreasing, so the Mach number will go down, right? Therefore, the this term stagnation pressure decreases. I hope this is clear.
Okay, sir.
Huh.
Clear.
Right. So let us move with the question now. So after the compressor, the temperature is known. Now let us calculate what is the pressure after the fan. Okay. Now let us calculate the properties across the fan. So across the fan, it is given that the right. So across the fan, it is given that the efficiency of the fan is given, and also it is given the pressure ratio of the fan also is given, right? So this is okay. I think yeah, pressure ratio of the fan is given, which is 1.6305. Okay. So with this, let us calculate what is P naught 7 by P naught 2, which is 1.6305, which is, and then if you substitute, you will get 220.6 kilopascals. Okay, and again, to find the temperature T naught, yeah, it will follow the same procedure, that you have the efficiency of the fan. So right. So what you do is, this is T naught 2, this is T naught 7 dash, this is T naught 7. So efficiency of the fan is T naught 7 minus T naught 2 dash T naught 7 minus T naught 2. Okay, and also it is if you take T naught 2 as common, so okay, so what you will get is yeah. So you can you use the above two relation, and you can get the efficiency. Okay, T naught 7 as yeah, now you can get T naught 7 as T naught 2 into P naught 7 by P naught 2 gamma minus 1 by gamma minus 1 by efficiency of the fan. The fan, right? Plus one. So this is similar to this same thing that we have done here. So this is I have done in a single step. So if you calculate this T07, so you will get this thing as 373.7 Kelvin. Okay. Uh, yeah. So let us write these values again: 220.6 and 373.7. So after the fan, so this is after the fan. This is 220.6 P naught, and T naught is 373.7 Kelvin. This is kilopascal. Okay. So now let us okay. So can somebody tell me what is the meaning of bypass ratio?
Mass flow rate in the cold path to the mass flow rate in the hot path.
Right, exactly. So this is given as 3, right? So uh, also this is given mc plus m hot is just okay. This is dot mass flow rate. This is just a cold air, right? So if you take m dot h as common, you will get mc by m dot hot plus 1 by m dot a. Okay. So m dot a is given. So m dot a is given as 74.83 kgs per second. So 74.83 divided by 4, because bypass, this is bypass ratio, this is given 4. So this is m dot hot is, so 74 point, yeah, if you calculate this, uh, you will get as okay. So this is 74.8354. This is 18.7075, and m dot cold is the it is just minus 18.7075. So this is 56.01225 kgs per second. So okay. So okay. Also, let us calculate what is the the pressure at after the okay. Another thing that is there is that is known as split ratio. So anybody know what is the split ratio? Any idea? Okay. So a split ratio basically is what percentage of air after. So this is the bypass duct. Okay. This is the cold air. So so what percent of this mass flow rate is going inside this cooling duct? So this, so if I write this, so this is mass flow rate of inside cooling duct, inside cooling duct by mass flow rate in bypass duct. Okay. So this is given as, I think this is some a small value, that is 0.25, I guess. So okay, split ratio is 0.25 here. So this is 0.25. So now the mass flow rate through the cold nozzle will be 0.75 times mass flow rate of the cold stream and mass flow rate through the bypass duct, the uh, the the cooling duct will be 0.25 times of mass flow rate of the cold stream. So okay, so you have to tell this is thus the 14.030 kgs per second. So yeah, okay. So right. So this is 0.75 times of m dot c. This is as 56.01225. This is 42.0091 kgs per second. Right. So you know what how the mass flow rate is going. So this, if I make a diagram, so this is your after the fan. So this again, this is getting split into two parts. This is the cool nozzle. So this is the bypass duct that is getting, this is used for cooling. This again mixed with, this is the fan, and this is the combustion chamber. This is the turbine. You have compressor. So this mix and this goes through a hot. This is a hot flow. This goes through a CD nozzle. Okay. So this is the, okay. If I mark the mass flow rate, so this is okay. So this will be seven. This is 74.83 kgs per second. This is getting split into 18.7075 kgs per second. This is 56.01225 kg per second. This thing. Then again, this is 42.0091 kg per second, and from here it is 14.0306 kg per second. Also, in the combustion chamber, you will be having some mass flow rate, right? Mass flow rate of the fuel. So at this point, you will be having some 18 plus 14 plus m dot f that goes through the hot stream. Okay. So this is the mass balance through the complete engine. Okay. So let us move to the combustion chamber part. So also now it is given that let us calculate what is P naught 4 by P naught 3, and it is given that the, okay, so P naught 3 you have 2030, so P naught 4 will be 1928 kilopascals. Okay. To calculate the mass flow rate of the fuel, you have to do energy balance across the combustion chamber. So you have m dot hot stream, then you that is, okay. So this is a mass flow rate to the after the combustion chamber. This is a combustion. This is a compressor after the compressor, and you have mass flow rate of the fuel. This is T naught 4. This is T naught 3. Right. So if you write this m dot h into T naught uh, 3 plus m dot f into delta h f is equal to m dot h plus m dot f into T naught 4. Okay, there will be cp. So right. So after this, if you calculate from here, if you calculate what is m dot f, you will if you will get as 1.574 kgs per second. Okay. So your T naught 3 is known from the previous uh, equation, that is 724.7. So this is, and this is also given, this is 1328 Kelvin. Okay, so with this, and this is known, 41400 kilojoule per kg. Okay, if you substitute this equation, and the only unknown is this m dot f, and you calculate this, you will get 1.574 kgs per second of fuel. Okay, so okay, so let us calculate for the turbine part. Okay, so for turbine, we need what is the temperature after the turbine, right? So can somebody tell me how to do that? I think we have discussed this thing in the previous class. How to calculate this T05, because pressure ratio across uh, turbine is not given. Can somebody tell me how to calculate it? Any idea? Okay. So what we do is, one thing we know from this equation is, from this diagram, is the energy that is being developed by the turbine is consumed by the compressor and the fan. So everybody agrees on this, that the energy that is produced by the turbine is consumed by the compressor and the fan, right, through this shaft.
Yes, sir.
So if you do this energy balance, so the energy that is going after the turbine is m dot a plus m dot f into cp into t naught. This is, yeah, this is station number 5. So this is t naught 5 m dot a plus m dot f cp t naught 4. This is the energy that is developed by the turbine. So only a part of it uh, will be used by the compressor and the fan. So we have efficiency of the shaft, uh, then, which will be equal to the mass flow rate of the mass flow rate of the air, then to cp, because all the air is passing through the fan, right? So then this will be 74.83 kgs per second. Okay, okay, this will be the hot stream. This is cpt naught, and yes, so right, so this is okay, this is t naught 7 minus t naught 2 plus m dot a into the bypass. Okay, this is the hot stream, right? Mass flow rate of the hot stream into cp t naught. It is, I think it is, yeah, t naught 7 minus t naught 3. Yes, yeah, yes, it is t naught 3. Okay, so right. Okay. So in this equation, your m dot a is known, m dot h is known, cp it is known, and it will be cancelled off if you assume after the combustion cp does not vary. So yeah, t naught 7 is known, t naught 2 is known, and t naught 3 is known. T naught 4 is known, and all the mass flow rate is known, and it is known. Only the unknown is T naught 5. If you substitute this, all the values in this equation, you'll get T naught 5 as yeah. If you substitute this, you'll get T naught 5 as 895.5 Kelvin. Okay. Now we have to calculate what is the pressure. So for a turbine, so this is the actual temperature. Yeah, this is 1328. This is 895.5 Kelvin. So okay, this is T naught 5 dash. This is T naught 5. This is T naught 4. Now efficiency of the turbine is given in the problem, which is yeah, efficiency of the turbine is 85%. 85%, which is T naught 4 minus T naught 5 by T naught 4 minus T naught 5 dash efficiency of the turbine. So now just substitute. Okay, uh, 1 minus T naught 5 by T naught 4 dash 1 minus T naught 5 by T naught 4 efficiency of the turbine. This thing can be written in terms of pressure because it is an isentropic process. Uh, this part is isentropic, so we can write in terms of pressure. So this is T naught 5 by T naught 4 by 1 minus P naught 5 by P naught 4 to the power gamma by gamma minus 1 efficiency of the turbine. So if you calculate what is P naught 5 by P naught 4 through this equation, you will get this the value around 1 point. Uh, yeah. Okay. If you calculate P naught 4 by P naught 5, you will get as 1.3286. Okay. So P naught 5 is 216.2 kilopascals. You can verify these values. I'll share this uh, uh, notebook with you, so you can after the class you can go through this slide through the notes, and you can verify of your own. Okay. So after this, after the turbine, uh, after the turbine, you have one cold stream and the hot stream that is getting mixed to get the to get the properties at 6. Okay, so how should we go ahead to calculate what is properties at 6? Any idea? How do we calculate what is the temperature after mixing? Okay, so I'll draw it again. So you have a cold stream, you have a hot stream, and they mix in a duct, and they then pass on. So you have to calculate what is T naught here. T naught for this is given. This is T naught 7. This is T naught 5. Can you calculate what is T naught 6? What should we do for this? How should we go ahead? Any idea? Also, the mass flow rate is given.
Like a weighted average.
Not a weighted average. Yeah,
Mass
actually,
average.
come again.
Mass average.
Yeah, mass average, or you can say you have to use the energy balance, right?
Yes, total energy upon total mass flow.
Exactly. Yeah. So Okay, so okay, let us see what is the amount of this is the hot stream plus mass flow rate of the fuel into the CP. Then you have T naught 5 plus you have this uh, mass flow rate to the this bypass duct, right? This is 14 kg something. So this is bypass duct. Then CP, you have T naught. What was the station? This, I think this was station number 7, right? Yes, this was station number 7. So this is um, T naught 7, which will be equal to m dot h plus m dot f plus m dot bd into cp into T naught 6. So you can calculate what is T naught 6 with this equation. So with this, you if you calculate this, you will get T naught 6 at 680.3 Kelvin. Uh, yeah. Also, yeah, right. So also also it is given that the pressure ratio for the duct is given as pi d. Duct is given as 0.97. So this is equal to P naught 6 by P naught 7, which is equal to 209.7 kilopascals. Okay. So let us write the values actually. Maybe it will be easier for us. Okay. Maybe. Right. So where were we? So yeah. So after the compressor, what was the temperature and pressure? This is 724. This is T naught is 724.7. P naught is 2030. Okay. Uh, After the combustion chamber, the temperature was yeah, after the it is 1328, right? 1389. So this is 1389 Kelvin. P naught was 1928. Okay. So after the duct, so you the temperature T naught remains same. Okay, because you're not adding any heat to the system, and P naught at this point is just 0.97 times of this. This is 209.7. So yeah, so this is 209.7 kilopascal. Okay, so right. I hope till this point everyone agrees with what we have done. Any doubt in any part of the calculation?
No, sir.
Okay.
No, sir.
Okay.
So just one doubt.
Come again.
The other person was asking.
Okay. Okay.
No doubt, sir.
Okay. Okay. So let us.
Sir, just
Yeah. Yeah.
no.
Sure. Please.
Uh, Sir, the mixing reduces the temperature, right? So if the temperature reduces,
Huh.
then the velocity will reduce. Means the final jet velocity, hot jet velocity. Then
Yes.
the hot jet
Yes.
thrust will reduce.
Yes.
So why do we mix it, sir?
Okay. So right. So after we need one bypass duct so that the outer casing that is there can be cooled. So okay, in generally what we do is we have a combustion chamber, and inside the combustion chamber we want the walls to be cooled. Okay, so we have some liners here. Okay, so this air passes through this, and this cools the wall of the combustion chamber. Therefore, we require this hot stream. Also, these part are used to cool the turbines also, turbine blade. Okay, so we need this part of duct for our purpose. So in actual case, you will be having so this part is known as bleeding. Okay, and there are some dilution holes that is there in the combustion chamber. Yeah, so this part is used for the cooling purpose. In this analysis, we have not assumed that a small part is getting bleeded, because the calculation would have been more tedious. Okay, so
Okay.
uh, the main purpose is for the cooling it. So that's why a small 0.25 times of the cold stream is taken into account. You can see the magnitude of this, right? 14 kgs out of this 56 kgs, right? Is used for cooling. Okay, so let us move ahead. Let us calculate what is the uh, which is known as primary nozzle. Okay, so the primary nozzle is a CD nozzle. It is a CD nozzle. Okay, and it is given that it is perfectly expanded. Okay, so let us calculate what is your T8. Okay, uh, T8, that is the T naught P8 by P naught 6 gamma minus 1 by gamma, uh, right. So if you calculate, you'll get okay, T naught, this is T naught 6. So if you calculate, this is 559.7 Kelvin. Okay, uh, and right. So this is if you assume that it is an isentropic flow. Okay, but in real case, okay, this P8 is just 101.325, and P naught 6 we know. Okay, this is 209. And right. So yeah, so with this we have T8, assuming that it is isentropic flow, but efficiency of nozzle is given. So this will be equal to the, okay, let us call this thing as T dash. Then this is to T naught 6, efficiency of the nozzle, T naught 6 minus T8 dash. So this is this same equation that is there across the nozzle. This is since we are expanding it, this is T8 dash, this is T naught 6, this is T8. So using the efficiency of the nozzle equation, you'll get this T8. So T8, if you calculate, this is 564.5 Kelvin. And if you have to calculate what is velocity at exit, just have to use this energy balance to, okay, let me write what is, so this is T naught 6 is equal to uh, T naught 6 is equal to CP T naught 6 CP T8 plus V8 square by 2. So if you substitute this equation, you will get V8 is equal to uh, V8 is equal to okay, Cp can be written as gamma r by gamma minus 1. You have 2, this is T naught 6 minus T8. Okay, so V8 from this equation you will get as 470.4 5 meter per second. Okay, let us calculate what is Mach number at 8. So this is V8 by gamma T8. So if you calculate, you will get 1.058. Okay. So now for the thrust you need what is a T8, right? So what is the area at the exit? So you have mass leaving the station 8, which will be your hot stream plus mass flow rate from the bypass duct plus mass flow rate of the fuel. Okay, and you have rho 8 u8. Rho 8 can be calculated by pressure P8 by RT8. So A8 you will get as
Sir,
uh,
can you please little scroll down
huh,
uh, a little further, sir, to can see the calculation? Yeah. Okay, sir. Thank you.
okay. Yeah, please let me know if I'm rushing or if you missed any part. Huh?
Okay, sir. No, sir.
Okay. So I think I hope you have seen this part, right? What we are doing here. So yeah, this is a
Mm.
long question. Probably you will not expect this thing in your assignments, but yeah, it will be a good learning experience for you all because it gives you a overall picture how you do a cycle analysis for a turbofan engine, right?
Okay, sir.
Uh,
Okay.
so if you calculate this A8, so right. So from this row 8, if you calculate, you will get as 0.6252 kg per meter cube, and yeah, area you can if you calculate, this is 0.4259 meters square. Okay. Now on, okay. So the thrust for the equation for this part is thus m dot 8 u8 minus m dot a into u inlet, right, plus a8 p8 minus pa. This is your hot stream, the thrust developed by the hot stream. How about the cold stream? This will be it will be similar, right? M dot 9 into u9 minus m dot 9 into ua plus a9 p9 minus pa, right? This is a cold stream. I hope this part, the thrust equation is clear to you all. Till now, what we have done is we have calculated what is M8. M8 will be just this part of the equation. This is M8, M dot 8, right? U8 we have calculated. This is 470 meter per second. This is V8. M dot A is given 74.83. UN we have calculated based on the Mach number of the flight. Uh, A8 is calculated. Yeah, and yeah, P8 and PA we okay. It is assumed that it is perfectly expanded, so this term will go off, not required. Huh? So, but anyways, we have calculated what is the area required for this nozzle. Okay.
Sir, just one doubt, sir. Hello.
Huh, huh.
Sir, why U6 is considered as 0? Sir, in our expression of U8,
Huh.
what happened to the velocity
Yeah,
part of the equation?
that is taken care of by T naught 6, because T naught 6 is T6 plus V6 square by 2 CP.
Okay, sir. Okay.
Is it fine?
Okay, sir. Yes, fine.
So, okay. Now we have to calculate what is m dot 9. I think we have calculated this. This is just 0.75 times of this mass flow rate through the cold stream, right? M dot 9 is known. This is known. Only the equation that we require is U9. And what is P9 and A9, right? Let us calculate this for the fan nozzle. Okay. So so let us find what is the critical, whether the nozzle is choked or not. So critical Mach number, the critical pressure is just P07, 1 plus 1 minus gamma by efficiency of the fan 1 plus gamma. If you are wondering how this equation came, this we have derived in the previous class. So you can find this thing on my this YouTube channel, or the link that is given. So yeah, if you calculate what is critical pressure with this point, so you will get 112.5 kilopascals. So this is greater than 101.325. Therefore, the nozzle is choked, right? Okay. So now let us calculate what is T9. Okay. So T9 will be, since it is choked, so the Mach number will be 1. So right. So this is, we can say that T9 is equal to T naught 7 1 plus gamma minus 1 by 2 M9 square. M9 is 1, so you can calculate what is T9. I think yeah, this will be divided. So so T9 you will get as 312.1 Kelvin. Uh, yeah. Now let us calculate what is U9. U9 is just 2 Cp T naught 7 minus T9, right? So with this you will get 353.4 meters per second. Okay. So U9 is known. Now let us calculate what is A9, area at the exit. So area at the exit is M dot 9 by U9 into rho 9. So if you calculate this, you will get this equation as, okay, rho 9 is just P by RT, P9 by RT, which is 1.257 kg per meter cube. So this value you just uh, substitute and just see. Huh? So your U9 is known. This is 353.4 meter per second. M naught 9 is 0.75 times of this. So yeah. So this is 42.0091. So this thing is 42.0091 uh, kg per second. So with this, if you calculate, you will get the A9 as 0.3793 meters square. Okay. So now only the equation that we require is for the thrust. So this is right. So this is m dot 8 u8, same equation, this which we have written here. So let me copy this. So let me copy this equation. And paste it here. So right. So if you substitute all those parameters, you will get thrust as yeah. So you will get thrust 53 53,300 newtons of thrust. So okay, so for TSFC, how TSFC is defined? Uh,
Dual mass flow rate divided by the thrust.
Thrust But yeah, so for this, if you calculate this, the value will be very small. So what we do is we generally write this thing in terms of R, right? So we multiply this thing in 3600, so the unit will be kg per Newton R, right? So this much kg is required per unit R to get 1 Newton of thrust, right? So if you substitute this equation, this is 1.574 by 53,300 into 3600. So you will get 0.1063 kg per Newton R. Okay. I hope this example. I know this was a little tedious, but it might have given you more insight what is going on and how we do the calculation. And so what is a bypass ratio and what is split ratio, right? So
Yes, sir.
so if you have any other doubt, you let me know. Right? You can ask me now.
Sir, one doubt.
Huh.
In nozzle and diffuser also total pressure is constant, sir?
Total pressure,
Because,
no. So it decreases. So in diffuser and in the nozzle, the total pressure decreases because of the boundary layer formation.
so the total temperature, sir, that remains constant like a constant area duct.
Yes, it remains constant.
Okay, sir. In all the cases of duct, total temperature remains constant and the total pressure drops.
Yes,
Right, sir?
yes.
Yes.
So whenever the friction is there, the total pressure will decrease. However, if you're not adding any heat or any work to the system, the total temperature will not change. Okay.
Okay, sir. Okay.
So
So whatever the pressure is dropping due to the increase in velocity is only a static pressure, right, sir?
yeah, no, it is a total. Yeah, it is a no. So what we are saying is, whenever the static, okay, so whenever they define these efficiencies, so it is the total pressure that is getting dropped. So why the total pressure is taken into account, because it takes into account for the velocity change also, right? So uh,
So suppose in nozzle
uh,
the velocity increases.
uh,
So because of that, some pressure should drop now, sir.
pressure will drop. Yes.
So
Yes.
that is a static pressure.
uh, Both will drop actually. So in a diffuser, the pressure will increase, static pressure will increase. However, the stagnation pressure will drop because the velocity in a diffuser is decreasing. So the static pressure has to go up. However, because of the boundary layer and the friction losses, the stagnation pressure will decrease.
So both in the case of diffuser and nozzle, total pressure will come down.
Total pressure will come
But
down, but it depends on the geometry. In case of a nozzle, your velocity is increasing, your pressure will decrease, and your stagnation pressure will also decrease because of the losses.
okay, sir. Okay.
Huh. Okay. So okay, any other doubt?
Sir, for the previous lectures note, I'm not unable to. Sorry, I can't open them, sir.
Okay, you cannot open them. So I have given the permission actually. So okay, I'll look into that. So probably so 1 minute. So okay, I'll look into that.
If I'm opening them, what I'm getting is tutorial 2, and this folder is empty. So.
Tutorial 2 is there, right?
Yeah, but no. What I'm getting is tutorial 2 folder, and the message is this folder is empty.
Okay. I understood. Let me check and I'll give.
I
elaborate
think
when
this
it's
is for
ready.
all other lectures notes
Ha,
also.
ha, I'll get. And even you can, I think YouTube link it will be working, right?
Yeah, the YouTube link is working, but I just thought,
Okay, okay. I'll look into that. If any, maybe the permission issue is there, I'll clarify that. Yeah.
okay.
Okay. Anything else?
Sir, not related to the today's session, but like after the total overall course, uh, will we be able to like publish a research paper on some topic related to this, or does it
Uh,
require further advanced knowledge?
yeah, you will get a yeah, you will get advanced knowledge, but for research paper I am not sure, because for that I think you have to read what, so these things that is that you are learning now, it is already there. So I do not think that you will be able to publish after going through the lecture, but yes, you will be getting enough knowledge to go through the research paper, which is getting which recent work that is going on. So after that, yeah, you can you have to read research papers for that.
Yes, sir.
Uh,
Also, could you give us some practice problem to solve? Because the current problems are like way too big, and I don't know if I will be able to complete them in tests, sir.
I understand. I understand. So maybe I'll refer you some of the books. And I think you can go through them. So there are some books like Flack. This is Fundamentals of Jet Propulsion. Okay, that is Ronald D. Flack. Okay, so there is one book. Another is Gas Turbine Propulsion by Mattingly. Another, if you want another one, there is Mechanics and Thermodynamics of Propulsion by Helen Peterson. So if you want, I can yeah, I can write in the chat window. Okay. Huh?
Yes, sir. Please.
So this is. I hope you can see this.
Yes, sir.
So another one is Mechanics and Thermodynamics of Propulsion by Helen Peterson. So the other one, the last one is, I think it is. So the book name probably uh, Elements of Propulsion, I guess. Yeah, right. So these three books, I think it will be sufficient for you to get a good insight on this aircraft propulsion. If you want a book on this, because most of the part that is there, it is a gas dynamics. So gas dynamics also, there are very good number of books. Probably yeah, Anderson is a good book. Yeah, you can follow Anderson. Like, so I think these three, you can go to for problems. First book is very nice. It has unsolved as well as the solved problems also. You can try with this. For more details on different type of theories and all, you can follow Helen Peterson and Mattingly.
Okay, sir. Thank you.
Yeah. Okay. Okay. Any other?
Okay. No, sir. Thank you.
Thank
No,
you.
sir. Thank you.
Bye. Good day.